Welcome to my 40th tutoring session in A-level chemistry. In this video, I'll give a brief explanation about the order of bond strength and bond energy. Don't forget to subscribe my channel, share, like, comment, and watch the full video. What is bond energy? Bond energy is a measure of strength of the bond, and bond energy is defined as the amount of energy required to break the bond. Bond energy values are expressed in kilojoules per mole or kilocalories per mole. And one can assess the strength of the bond by its bond energy values. Here's a table depicting the bond energy values of different types of bonds. In case of van der Waals forces, the bond energy value ranges from 0.4 to 4 kilojoules per mole. In case of hydrogen bond, the bond energy values range from 10 to 40 kilojoules per mole. In case of covalent bond, the bond energy value varies from 150 to 1100 kilojoules. While in case of ionic bond, the bond energy value varies between 400 to 4000 kilojoules per mole. Now looking at the bond energy values of these different types of bonds, one can clearly state that ionic bond is the strongest, while the van der Waals force is the weakest. So more energy is required to break a stronger bond, while less energy is required to break a weaker bond. So that is about the bond energy and bond energy values. Now what is bond strength or strength of the bond? Now bond strength or the strength of the bond indicates how strongly the atoms are held together in the molecule. Let me explain the significance of bond strength and bond energy with some examples. 347 kilojoules per mole of energy is required to break the carbon-carbon single bond. 614 kilojoules per mole of energy is required to break a carbon-carbon double bond, while 839 kilojoules per mole of energy is required to break a carbon-carbon triple bond. The carbon-carbon triple bond in alkynes is much more stronger than the carbon-carbon double bond in alkenes. While the carbon-carbon double bond in alkenes is more stronger than carbon-carbon single bond in case of alkenes. So what is the key takeaway from the discussion so far? Now the key takeaway is that the carbon-carbon triple bond in alkynes are more stronger than the carbon-carbon double bonds in alkenes, which is much more stronger than carbon-carbon single bond in case of alkenes. So that is to say, more energy is required to break a stronger bond, while less energy is required to break a weaker bond. And therefore, the carbon atoms are strongly held in case of alkynes, while the carbon atoms in case of alkanes are weakly held. Here is the order of bond strength from weakest to strongest, with van der Waals force being the weakest and the ionic bond being the strongest. Though the hydrogen bond is stronger than van der Waals force, it is much weaker than covalent and ionic bond. Let me begin with the van der Waals force. Now, van der Waals force is the most predominant intermolecular force between non-polar molecules like alkenes. How do the van der Waals force operate despite the non-polar nature of the alkane molecules? Now, van der Waals forces, they result from temporary dipoles that occur due to fluctuations in electron distribution within molecules. Let me explain with reference to the non-polar noble gas helium atom. In the neutral helium atom, you will find 2 protons in the nucleus and 2 electrons in the outermost valence shell. So in a neutral atom, the electron is evenly distributed. But due to momentary or temporary fluctuation of electrons in the atom, you will find that there is uneven distribution of electrons. And this leads to clustering of electrons towards one side of the atom, leading to development of dipole. Now, when this helium atom A with dipole, when it approaches a neighboring helium atom, there is enormous amount of repulsion between the electrons in the outermost shell. As a result of repulsion between the electrons in the outermost shell in these two atoms, it induces a dipole in the neighboring helium atom B. So a dipole is induced in the neighboring atom B. So now you've got atom B with induced dipole and atom A with induced dipole as well. So as a result, there is mutual attraction between these two helium atoms with dipoles. Now the same principle or mechanism holds good even in case of non-polar molecules like alkenes. So in case of alkenes, the van der Waals forces result from temporary dipoles that occur due to fluctuation in electron distribution within molecules. And a bond energy value of 0.4 to 4 kilojoules per mole is required to break this bond. So van der Waals forces are the weakest of the bonds, which is reflected in their low bond energy values. Now moving on to the hydrogen bond. Now 21 kilojoules per mole of energy is required to break the hydrogen bond between the water molecules. A hydrogen bond is a dipole-dipole interaction or dipole-dipole attraction or intermolecular force or electrostatic attraction between positively charged hydrogen atom that is covalently bonded to electronegative atom in one molecule that interacts with a electronegative atom with a lone pair of electrons of another molecule. So 21 kilojoules per mole of energy is required to break this dipole-dipole interaction between the water molecules. That is the hydrogen bond. And what about the covalent bond? Now covalent bond, as we all know, is formed by equal or unequal sharing of electron pair between the atoms by overlapping of atomic orbitals. Now there are two types of covalent bonds. One is the polar covalent bond and the other is the non-polar covalent bond. In case of polar molecule like hydrogen fluoride, 569 kilojoules per mole of energy is required to break this polar covalent bond. And what is the reason for this polar covalent bond in case of polar molecule like hydrogen fluoride? The reason is the more electronegative fluorine atom, it tends to attract or pull the shared pair of electrons closer to its nucleus, and as a result, the fluorine atom acquires a partial negative charge, while the hydrogen atom develops a partial positive charge. And this leads to development of a dipole. So 569 kilojoules per mole of energy is required to break the polar covalent bond in case of hydrogen fluoride molecule. What about non-polar molecule? So in case of non-polar molecule like hydrogen, 436 kilojoules per mole of energy is required to break the covalent bond. And in case of non-polar molecule like hydrogen, covalent bond is formed by equal sharing of electrons between the hydrogen atoms due to overlapping of the atomic orbitals. So why it is equally shared in case of non-polar molecules like hydrogen? Because the electronegativity values of both the atoms are same, and moreover the atoms are identical, and therefore the electrons are equally shared, resulting in a non-polar covalent bond. And an average bond energy of 415 kilojoules per mole of energy is required to break a CH bond in case of methane molecule. Now moving on to the ionic bond. How is the ionic bond formed? An ionic bond is formed by a complete transfer of electron from one atom to the other, resulting in the formation of positively charged and negatively charged ions. So in case of sodium chloride salt, you will find the ionic bond is formed by a complete transfer of valence electron from sodium atom to the chlorine atom, resulting in the formation of positively charged sodium ion and negatively charged chloride ion. It is the result of strong electrostatic force of attraction between the positively charged sodium ion and negatively charged chloride ion that holds the ions together. And therefore, enormous amount of energy is required to break this ionic bond. Nearly 769 kilojoules per mole of energy is required to dissociate 1 mole of solid sodium chloride into gaseous sodium ions and chloride ions. The unit cell of sodium chloride is in the shape of a cube, and the unit cell of sodium chloride represents a repeating unit. When stacked together, it results in formation of the crystallotic structure of sodium chloride. The high melting point of sodium chloride shows how strong the ionic bond is in case of sodium chloride. So a high bond energy of 769 kilojoules per mole in case of sodium chloride reflects the strength of the ionic bond. Thank you so much for watching my video. I hope you enjoyed it, and I'll meet you in my next interesting tutoring session.